production, and he's one of the organizers, so he's in charge on all the good stuff.
He really does.
I can turn this off, I think. All right, good afternoon. Pleasure to be here today, and I trust you have had a good week so far. So what we're going to do is kind of two things. I'm going to start with kind of picturing a broad image of how computing can evolve and where we might see it going as today and going forward in the future. And then we realize that it's going to be really hard to accomplish this, so there's a bunch of challenges. And then the question is, what can technology do to help us to address some of those challenges? And what is the path forward that we might imagine? So I titled this the compute continuum and its energetics. So the continuum is the vision. The energetics are really the problem. All right. So again, let me kind of picture this by going backwards a little bit. For those of you who are old enough, and I look at some of you are, you remember the time of how computing was basically individual elements, computers. Ultimately, we started putting some networking in with thick cables. We connected the computers together. And sure enough, some wireless started to emerge, but it was all analog, and you only could do voice. Right? That was the 1980s. Things changed. Obviously, in the 90s, we start seeing wireless devices, mobile devices emerge. And they became part of the picture. So now we have, on one side, compute centers, where we had the computers basically centralized, and then a bunch of active devices, mobile devices that connected to it, either wired or wirelessly. And the interesting number is that this rapidly grew into some large type of platform. Think about it, billions of connected mobile devices connected to that network. So that was the 2000s, approximately, 3G, and so on. Now going another 10 years, we started putting another layer around it. Sensors everywhere. Small sensors connected with wireless, energy self-contained, and battery connected to that same network. I call it the swarm at the edge of the cloud. And the numbers are even more interesting now. Obviously, we have millions of compute elements right here in the core, but we're actually talking about billions to trillions of connected devices together. But still, we consider this as a number of individual entities. You have mobiles, and you have sensors, and you have compute centers. In reality, they're all kind of one thing. What we really have building is a compute platform that is spreading around the world. Again, this is where we are now, where we have basically a network that connects everything and everyone. Humans are connected to it, we have sensors on humans, we have cars, autonomous cars, you name it, agriculture, environmental monitoring, you name it, one platform. So we really have to change our thinking here. We have to start thinking indeed of this as one gigantic computer that we can run application on. And it's really the idea of intelligence everywhere. So the compute continuum is really a connected ecosystem allowing complex application to be executed from the edge all the way to the cloud, and very often entertaining parts in each of that system. Right? So it also has the opportunity now, because now computation doesn't have to be stuck into one place. It can actually migrate and adapt based on the needs. So think about moving computation to where relevant data resides. Remember what Mark talked about yesterday, locality? So why keep the computation somewhere far away? Move it to the data, and you move it to the place where you have resources at a minimum cost. So think about this as a very dynamic environment. Obviously, AI will be everywhere with those things. It's obviously at the general intelligence place, the big centers, the huge centers that are being built right now, solving very big problems, like indeed science problems like protein folding, societal problems, large societal networks, and so on. And then you have the technologies that are helping humans, assisting humans, like your agents, as we were talking about, and autonomous cohabitants, cars, robots, you name it. And then finally, all the way down to the human himself. There are wearable devices, and potentially implantable devices, brain-machine interfaces, is all part of that big picture. And all of them are using some form of AI, combined sometimes with real intelligence. Okay? So that's the picture that you have to keep in mind, that what computing has become or is becoming. Now, if you look at the killer app to me, the killer app is really creating a mirror world. With all those sensors in the world, we're measuring what's going on. We're getting information continuously of the active state of the network and what people are doing. And using those sensors, we can feed it into a model that runs simultaneously on somewhere in your cloud or wherever you can run it. That basically keeps an image of what the reality, it's kind of a virtual image of what's happening in the real world. But it's not sufficient. It doesn't only create an image, it also feeds back information backwards and controls what's going on in the world. So it's a closed loop system that basically forms a bidirectional bridge between physical and virtual. So that's the mirror world kind of concept. And you can think about many different applications of this. Obviously, one of them, a very obvious one, is mobility. So we have autonomous entities like semi-autonomous entities like our cars. But our cars can only know what's around it. You only see as far as your sensors go. You don't know what's behind the corner or at the other side of the town or what's going on there and how things are moving. So you have the big picture combined with the local picture. That's a perfect example of a mirror world where you basically model on one side how traffic is flowing and you pass that information back to the cars. So again, a closed loop system. So you can think about many applications. This is also happening in agriculture and environmental monitoring. Mobility I already mentioned, health and wellness for sure. We're monitoring basically what's going on in our body. We have information, we have the big picture of what do these symptoms really mean and what can I do about it. Automation manufacturing, system design and operation. Another one, energy networks, power delivery, all those type of things, weather and climate. These are all perfect examples of mirror world instantiations. And obviously humans are part of this. We often think about this as something that's but I believe there's a very strong interconnection between humans. And again, this is formed by the network around our body that measures what's going on, gives us information back as well as. So the humans are a big part of this, and we control what's going on in the network, but at the same time getting continuous information. And here's some examples, like digital twins on your health case, but also like how humans live in the world, adaptive environments for people that have basically deficiency, people that have elderly people, and so on and so forth, brain-machine interaction, all those kind of things. All right, so that's the background. So this is cool, but the question is, what does it take to build something like that and to maintain it? So let's look forward a little bit. Sensor explosion. We're actually putting sensors down at a phenomenal rate. Like always, it's an exponential. So if you think about it, as a human, we process about 70 gigabytes of information per day. As a single person, but all your sensors, what you're inputting, primarily coming from vision, obviously, but also from touch. These are your two key elements. But as we think about it, that's pretty much a constant, right? Per human, that's pretty much a constant. It goes up a little bit. We get better in accessing information over time. But this is the projection of the total number of data acquisition by sensors that are going to be submitted in the world. That's a huge number, 1 brontobyte per year. So think about it, brontobyte is a great number. Probably for some of you, it's the first time you've heard this number. It's about 10 to 20 bits per second. Tremendous amount of information. So we have a problem with all that data that we need to process. Okay, we can get that data, but you have to transmit it to somewhere. So we have networks. Again, if I look at what I could transmit wirelessly, you see that we have an exponential curve. That's predicted, that the amount of data that we get with 5G, 6G, better optical networks, all those kind of things, how much data can we transmit, again, is exponentially increasing. But one thing that worries me is that the rise, let's say at the year 2030, we're going to have 3 to the 10 to the next 19 bits per second of acquisition, while the amount of data we can transmit is going to be only 5 to the 10 to the 16th. So we have a gap. We create more data that we can transmit, which basically obviously says that we're going to have some intelligence in the sensor itself. extract information and not basically data. All right? And then the amount of data we're going to store. You get all that data, you have to store it somewhere, so the question of storage is also going up exponentially. And we need smart storage, maybe new ways of storing information. People talk about DNA as a means of storing things. A lot of interesting ideas out there, but obviously another big challenge. We create more data, we basically need to process and store them as well.
How big is the Zeta compared to a Bronto? Like, these are all way above.
You have to figure out exactly how much that is. 1 to the 10 to the 18th, and the unit is in zettabytes. So I think 1,000 zettabytes is probably a Bronto byte. So phenomenal numbers that we basically are dealing with. And then obviously computation. Computation is going to require more and more as well. So for instance, you just want to build the metaverse, which is one example of a mirror world, obviously. And Intel thinks that the metaverse will need a 1,000-fold increase in compute power. This is great. But if you have the bigger picture, I want to basically create ultimately a visual or virtual model of the world, right? Can I do that? Can I have the whole physical world and create a model that runs in parallel? Fortunately, some people say it's impossible. The Earth's complexity is non-computable. The limits of scaling, loss, nonlinearity, and chaos basically tell us that Earth is a complex system because it instantiates life at a planetary scale. So trying to predict exactly and how this thing is going to run is going to take a computably interactable. Okay, so big challenges. World of challenges, actually, when you think about the scale and integration of the systems we were having. Fragmentation. The problem with a lot of those mirror systems are basically vertical pipes. Every company, every business are basically keeping their data in a certain column and they're not exchanging it. So fragmentation is always a problem. Very often, if I could mix information from various sources, I could get a bigger picture, but obviously business models and that basically make that hard. Robustness is going to be extremely important. Transparency, security, privacy, liability, ethics, you name it all. It's all part of the problem of basically this mirror world or compute continuum. But I'm going to talk about one thing specifically, the stuff I know about, is energetics. Energy to run a system like this. And again, you've seen those numbers many times before, but really we have a challenge. And the challenge is that indeed we have huge numbers. Cyber world is millions of centralized nodes, and probably pretty soon is going to be billions of them. Think about this, all NVIDIA style, most advanced chips, all stacked together in big time. Terabytes of data rates, mega gigawatts actually of power. And that's what we have here. Right now, they try to run as fast as possible. If you want to make money out of a data center or a compute center or an AI center, you want to make sure you can compute as much as you can and as fast as you can. So very interesting model there. And right now, they're pretty much still von Neumann-based computing. Even though they have data flow, engines, and accelerators, the big thing is still a von Neumann machine. On the other hand, if you interact with the natural world, it's very different. The needs are different. The environment is different. We might have also huge numbers. We might have those trillions of connected nodes. But the data rates that produces go from kilobits to maybe megabits per second or something like that. Not a huge amount. The power you want to consume there per node is as small as possible. And really important is we're running this as fast as is needed. There's no advantage to run too fast. You run basically based on the data. So you have kind of a gradient here between what's needed on this side and what's needed on this side. And both come with challenges. So let's think about the right side here, the compute center. You've probably seen this picture before. This is Lisa Su, who's the CEO of AMD at ISSC 2 years ago, where she plotted basically the amount of performance that is happening on supercomputers. But you can easily map that also to AI accelerator type things, very similar. So we're now at exascale. By 2030, 2035, we're going to be at a zettascale type machine. Now, the interesting number is here. The performance doubles every 1.2 years from a computational perspective. So that's good. At the same time, however, the energy that it takes, or the energy efficiency, is improving as well. So we see that we basically get an improvement, and at the Zeta scale, we talk about the 500 megawatt style machine. But the challenge here is that the efficiency only doubles every 2.2 years. Every 1.2 years, every 2.2 years, we have a gap. Efficiency performance goes up 100x over 9 years, while the energy efficiency is basically going only up by a factor 100 every 14 years. So the longer we go, the worse it gets. We're going to basically see a growing power implant footprint of the systems we're building. And again, this is nicely pictured in this image here. Shows the global data center power consumption by 2030, and you can see how it basically improved till this is right now. This is where we're going, and obviously AI is taking a big chunk of that. 152 nuclear power reactors to basically do that, or 236 natural gas plants, so 4.8 terawatt hours annually. That's a lot of carbon we're having to put in the air. So everybody talks, however, only about the data centers. I also want to talk a little bit about our sensors. The sensors themselves, they're very tiny little devices, and they don't consume much, but we get lots of them. And you see the numbers here. There's 80 billion connected devices to the network, but it doesn't, if you compute the number of sensors, it's a lot larger than that as well. So if you do a very simple analysis, 500 milliwatt per sensor node, and you have them at 50% duty cycle, you turn them on overnight, they don't run all the time. Yearly power consumption of 80 billion devices at 1.75 terawatt hours, which is 300 million solar panels and 350 gigaliters of lithium-ion battery. So those numbers are important as well. You have to be able to sustain that number just as well. So energy efficiency in those things is going to be very important as well. So that's the picture. We have a tremendous opportunity, but the tremendous opportunity comes with some demands. And we figured out how to deal with that. We have to close that gap that I just showed you. All right. Now, again, this is very similar to the slide that Mark showed you yesterday. This is the evolution of technology as it's gone. It's a little bit differently pictured. Overall, basically, this is the efficiency from an energy perspective for floating point 32. And we see it's gone up nicely. So compute efficiency still goes up a little bit, but not anymore. It's flattening out. Transistor density, the number of transistors can jam together, is still on the rise, but again, is expected to flatten out. What little density, the way we print those transistors, with these amazing machines in EUV and high aperture EUV machines, is also going to saturate out. We're going to have to figure out, it means that the thing we can print is going to basically be limited. And clock frequency, we know that a long time is flat as well. So technology itself, semiconductor technology is at a cross point. And it says, that's what it says here. This is from EE Times. It's an inflection point that will require transformation in silicon design, development, deployment. But the next big silicon supercycle will unleash life-changing innovation and decades of unprecedented engineering creativity. We have to be smart. We have to basically, if we go forward, we cannot just extrapolate from the past. That's the message, basically, that arises here. So here's kind of what my roadmap looks like. What I think is the type of things that will help us to get around that. Density scaling is what we have been doing for a long time. Parallelism, we figured that out a while back, good thing. Initially, people hated it, but now they love it. The more parallelism, the better, right? Customization, accelerators, again, a recurring topic. We basically, if you fit the hardware to the application, you're going to be more efficient. If you put a whole bunch of layers in between, you have layers of inefficiency. Okay? Heterogeneous packaging, basically making sure that you have different combinations of things together. I'll talk more about this. 3D and CMOS. 3D basically is definitely an important way out. And also the use of locality. Again, I'm preaching to the choir. It was mentioned already yesterday and previous days. Locality, sparsity is very important as well. Don't run things you don't need to run. And then new primitives are going to be a necessity. We cannot just keep on thinking we're going to do the same thing, new primitives. And to me, the other one is systems that run really intelligently. Again, think about the compute continuum, perform computing, where the cost is cheap, where the resources are available, and where the data is. That's really what you need to think about. So I'm just going to walk you through some of those things, going from here and show you some of the evolution. Again, some of it might be similar to what Mark has shown. This is a little bit more fancy from a graphics perspective, but it's the same thing. This is your transistor evolution up to the year 2042. And you might say it's a long way out, but there's places in the world, like IMEC, for instance, where people do a lot of thinking about what's going to be the next transistors, what can we do with any scale. So this is where we are right now. FinFET is the approach that we take for transistors. This is now little fins. But this is where we know are heading. Companies like TSMC are already going into this realm, what's called the nanosheet, where the transistor is kind of not a single fin anymore, but a couple of nanosheet layers on top of each other. Really hard to manufacture, not easy. And then after that, the next step is what's called the CFET. By the year approximately 2030-ish, we will see this emerge. By the way, prototypes are already running. People have shown this works. Where you put the PMOS transistor on top of the NMOS, or vice versa. So your gate is now a vertical gate and not anymore a two-dimensional structure. And they believe this will go till about 2033. So we have an evolution. We're not stopping. People are making things denser and denser and denser, but it's getting harder. Just that CFET is a nightmare. If you look at the complexity of the manufacturing of a device like that, crazy. After that, interesting questions, things to think about. What we're also doing is keep on scaling the density, right? So the amount of, the pitch of what we can draw is getting smaller and smaller as well. And we're adding more interconnect layers, more and more metal layers on top, but also, as we'll talk in a minute, metal layers at the backside of the wafer. You can actually, the wafer anymore is not something like you put transistors and then wires and wires and wires. By making the silicon really thin, we can go to the other side and start wiring on the other side as well. So a truly 3D structure. So again, this is good. Basically it says, don't really worry too much. We have another 10 years to go. But I'll also show that there's somewhere this is going to be expensive. It's not going to be cheap. So just to give you an idea what you get from all of this, every step, like going from the last step from 2022 and 322, we get about 30% improvement in density and about 30% improvement in energy. That's good. The next step is kind of a tweaking thing. It doesn't help much in density, but it helps to make it a little bit better from an energy perspective. But overall, by 2033, we might get a total reduction of 2 to 3 times in energy. So that's what you get. Remember, that computing thing is going up faster than that. That's not sufficient by any means, so we have to be smart. So question is where to go after. That's where a lot of people are thinking about. One thing that people about is, well, maybe 2D materials. 2D materials where you have one molecular layer, and that's your device, and you basically connect it from the top and the bottom. Again, there's some very interesting materials that are emerging. The nice thing about having all that AI stuff available is that material science has evolved spectacularly. People are making materials that you couldn't even dream about 5 years ago. So 2D devices is one possible. But bottom line, ultimately, we're going to run against this. There's only so much you can do in 2D, you have to go 3D. But there's some examples of those devices that people are talking about. This is indeed a 2D transistor. You can see one molecular layer, and your gate up on top, you can have a silicon dioxide beyond. It looks like a transistor, but it's a very, very thin one. And the question is, can I get enough current to this, and all this type of things. Another one that I think is interesting is you starting to use ferroelectric materials in your transistors, kind of magnets you can turn around. And they can help actually to make transistors that switch very nicely. And as a result of that, leakage goes down, which means that I can reduce my supply voltage. Maybe I can start thinking about logic at 200 millivolt or below. pushing the supply voltage down is a big one. And devices like this could help. But again, this is speculative. These are people are playing around. The university here in Berkeley, there's a big program in this whole space. So interesting things to look at. But again, this is what Mark already said yesterday. You have a problem. Those technologies are great, but they're expensive. If you look at the cost going up, basically just the die, plus the design cost, the NRE that goes into it. And it ultimately you say, okay, you want to get some gain. What's your total cost per chip, basically? And as you can see, it's going up substantially, going node to node. And the red line here is what the average sales price is for your part. So if your cost is, you have a problem. You cannot sell it to anybody anymore, and it's the end of the story. All right, so you have to find a way to get around that. Bottom line is, one of the things to remember of this is that if you want to basically beat that average price, and you want to get that NRE down as much as possible, what you do is create parts that you can sell a lot. If you're NVIDIA, you sell huge amount of parts of the same. But there's only a few companies that can do that. So the question is, can I think about architectures, hardware, that can be large volume, yet be dedicated to various application spaces? And I'll come back to that in a minute, the whole idea of, can I make reconfigurable silicon? That basically brings us from acceleration and dedication to that part of the market where I have huge volumes. Really important. All right. Again, this is kind of following up what some people already have said. One way to say, I'm not going to make those big wafers anymore. And by the way, I don't need that most advanced technology for every single part. Maybe for my processor core, I need very high speed, very high density, as much as possible. But for memory interfaces and things like that, you might need that much. There's multiple layers that basically can be slower. So the idea of a chiplet, basically taking smaller parts and putting them together using some interposer, is definitely a good way to go. It creates basically improved performance through specialization, because every one of those chips now can be doing a specific thing and have a technology which is optimized for it, rather than having to use this very expensive technology. So again, this is where the industry is going right now, full blast. And you see this happening in the high performance community, where any one of those things like NVIDIA and Tesla and all those guys, they're building boards now with these chiplets to get the highest performance type of modules. But if you go to automotive industry, they're doing the same thing. Their parts are very different. They have sensor interfaces, they need compute, all this type of things. So the automotive industry is going very rapidly also towards the chiplet approach. Customization, you make sure this customization is 3D and it's locality. By putting it all close together, I basically make it much more energy efficient. So that's clearly happening. It's no-brainer. But not in the longer term. So locality is kind of one of the things that comes out of that, basically, is one of the next steps that you automatically get from this 3D integration. And again, people have been doing this for quite a while. If you say, well, I've been stacking things and so on and so forth, so here's like how the flash memory looks like today. Today, the most advanced flash memories, 370 layers on top of each other. They're real 3D. And the nice thing about it, you can do this easily because it's very regular. You have these bit lines that are vertical, and you can really keep on stacking them on top of each other. Very dense, very beautiful. But there's other ways of doing locality. It is, for instance, doing optical. Optical is great because from an energy perspective, you can send a lot of bits at very low energy. Today, some of the best optical interfaces are going below a picojoule per bit, which is quite nice, and it's very high data rate. The other one is kind of already, and I'm not going to go much more into that, but it's mixing memory and logic together. In-memory compute, you heard about this yesterday, is one other option to go. But I would like to go to a somewhat different direction. Okay, so as I said, what we can do today is we can make wafers, and make them thin, very thin, a couple of maybe 100 micron. We can drill holes to them very nicely. You can make these pitches very dense. Today, maybe hundreds of nanometers of distance between those pitches, so maybe 1 micron of distance. So huge density, but that offers you the opportunity to create wafers with different functions. There might be one that is dense logic, which is the very expensive one. That's the one I'm basically going to use the most advanced technology. But I can have drive logic. If I want to basically put buses and things like that, I need bigger transistors. I don't need the fast transistor. I need bigger transistors. So you can use older technology to do that. Same thing for memory, multiple cache layers. You can use different layers. And on the back side, actually you can put some wiring here as well. I can do my power distribution at the bottom. And if I have some other space, I can put the I/O there as well. So you see this idea of a wafer stack. Some of them relatively cheap, other ones more expensive, and you smack it all together. Like this. What we call CMOS 2.0. You really think about. Now, the natural way to think about the design like this is, it's a bunch of 2D layers. But that's the wrong mindset. You really have to think 3D, like 3D chess, right? That's what you need to think about. So it's a hybrid integration of multiple technologies and functions, and choose the best technology for each function. But you need to rethink the primitive components and how you map it into the structure. How do you place them, route them, synthesize them, timing analysis, verification, all those type of layers change. So now it's not easy because our industry is built on doing a little bit better than the last time and improve incrementally. So now you have to go to cadence and synopsis and say, hey, you have to rethink a little bit the way you do things. But to me, this is a tremendous opportunity in the way to think about how we're going to build computing elements in the year to come. Now, you might say, this is going to be tremendously expensive, right? And it only can be done by, again, this few. But this is where the catch comes in. What can I do to create a part like this that indeed can have high volume, yet be very specialized for application spaces? And I think you heard the answer already before. I think is that, I call it we call it software-defined silicon, where you basically have a flexible canvas that you can program to basically do a variety of functions. So the canvas contains building blocks or grained elements. And then you basically reprogram it. It's not bit level, it could be processing style elements. And you can tune them by because, hey, I have memory, non-volatile memory right smack there on one of my layers. So I can reprogram the network and I can reprogram the functionality of the hardware. So reconfiguration or dynamic reconfiguration returned. Now, this is not new. I worked on a DARPA project in the 90s on reconfigurable hardware. And it didn't go anywhere because of the overhead of the memory that you have to put in there and all this kind of. But now if you have CMOS 2.0, you can stack those things very close to each other. Suddenly it starts making a lot of sense. So again, this idea of soft cores, that actually the software is going to determine what the hardware looks like. If I need another processor, bingo, I'm going to put one there. So that's an interesting perspective. And so improve efficiency through flexibility is kind of one of the mindsets here. So just think about this. Obviously, is far away. This is going to be 10 years out. But it's a bunch of people starting to play around and think about this. All right. You can do crazy things with your 3D as well. I think I like to show this. This is a company, a Dutch company, that does neuromorphic chip. They're trying to put neurons down. And remember, neurons, one of the key things I'll come back to in a minute, neurons are devices that have a huge fan-out. Compared to what we do in silicon, right now a single gate goes to 4 gates, and a neuron has about a fan-out of 1,000 to 10,000 other neurons. So how can I do that? Well, what they did is basically have the axons and the synapses basically as vertical rods, just like you do in flash memory. And they actually, by nature, every layer of their network is not the same. They put actually randomness in every layer in such a way that the network is kind of convoluted and not a regular network structure. But again, there's an idea of how you can actually heterogeneity to basically build a 3D brainy style structure is an example. Again, not easy to manufacture this. I'm not sure this company is ever going to survive, but it's a beautiful story.
But do they know how to use a structure like that?
Well, obviously neuromorphic, there's a bunch of people have been thinking about neuromorphic hardware for quite a while. And how to program them, how to learn, teach them, and all this kind of thing. So this is very similar. What it is a network of neurons, just like any neuromorphic style network. And they use backpropagation and all this kind of stuff to basically make the thing programmable, or basically to learning as well as doing inference. Yeah, obviously they need software if they want to make this thing into something useful. But you're right, these are important things, because so far, if you look at all the neuromorphic hardware that's out there, there's still issues with exactly how the learning process is optimized. I think there's by no means where it should be today. All right. Now, one thing that you might ask yourself if you start stacking all that stuff on top of each other is how they get the energy in and out, how they get heat in and out, and the heat out, energy in. Well, again, the advantage of the approach is that I now have multiple play around. This is the way we build chips today. All the transistors are at the bottom, very dense, and then you have layers of wires that are getting thicker and thicker and thicker. Because here you have to be able to connect to your transistors. The higher you go, you basically want to get resistance down. You want to get the capacity, basically get things as fast as possible. So thick wires on the top and narrow wires at the bottom. Now, if you now thin those wafers quite a bit, and I can drill through the silicon, why not put the thick wires at the bottom? Very close to where your transistors are. So your power distribution is at the backside of your wafer. And then you can say, well, maybe I can make it more intelligent. I can do a power switch network in there. Maybe this doesn't have to be at 500 millivolt where you need a lot of current. Maybe I can distribute power here at 10 volt or 20 volts or something like that. So you have far less current, which makes things a bit easier as well. So you can play games and you can start making, dynamic power conversion in the backbone. And ultimately, I can do some single wire buses in there as well. So that's an opportunity to think about how to do. You have to think about this power distribution as well. Okay. One more thing about locality. I think I've been doing a lot of thinking or working in the last couple of years on brain-machine interfaces and things like that. So I've been looking a lot at how our human brain works and trying to get some lessons from it. And as I already mentioned, one of the big things about the human brain is its interconnectedness. We have indeed, as I mentioned, the average fan out of a computer is 4, in the brain is 1,000. Which means that if you look at the network diameter, which is the average number of hops it takes to go from one node to the other one, in the internet, estimated value is about 10 to 15 hops between two nodes. In our brain, it's approximately 3 hops. So every neuron is relatively close to every other neuron. And we have 80 billion of those. So having very dense style networking that is, and 3D is kind of interesting. Also, look at these numbers here. The wiring density of our brain is actually better than what you will find basically on a particular chip. So locality, interconnected network density is something you can play about. And I think 3D will help, as I showed you with previous examples, to address some of that. But this gets me to the next or the last part of my presentation. Yes?
Did you say, ask energy density of the brain versus the computer?
Yeah, I have the numbers. So the brain on average, 20 watt. Volume is about 2 liters, and 1.5 liter, 2 liters. So it gives you an idea amount of power you have. And obviously, heat management is a very important part. The way we do it is we have our blood coming in, and the blood is also acting as a cooling. It basically takes the heat out of the brain and removes it. So we have a very efficient cooling system built in there, because otherwise you would have a problem. So the brain itself also does very careful power management. If you try to do too many things at the same time, you're firing too many neurons, the brain will slow down. So if you're really a multitasker and you think you can do more and more and more stuff, actually the brain will say, hey, my temperature is going up. Its average temperature cannot vary much around, it's at 37 and something. If it goes out of there, it starts shutting down functionality because it's very, very temperature controlled. But yeah, the energy system is actually quite beautiful, how it works. But again, it's an adaptive system. It basically figures out how much what it needs to bring in terms of energy in based on the functions you perform and the time of day it is. All right. So that brings us to the last part, as I said. Maybe we should, this is where silicon is going. We're going to go 3D, that's pretty clear to me. Larger density networks, locality, heterogeneity, all the stuff I think we've been talking about, accelerators. But to me, ultimately, it's probably worthwhile to think about, are there other computational elements that can help us to go forward? Think beyond transistors and digital gates. We're kind of stuck in a mindset. There's been a beautiful abstraction. It is an amazing abstraction. You basically start with gates, you get your Boolean logic, and from there on you can stack layer and layer and layer, and you don't have to worry about what's below, it works. So that's an amazing thing. Trying to copy that is not trivial. But I think it's worth to learn from biology and physics, looking at these other areas. And obviously we've done a lot already on the neural side. Think about what can we learn from the human brain, which is an amazing machine, 80 billion neurons, about 100 trillion synapses. By the way, the best NVIDIA chip is by no means close yet to this. There's another factor of 10 to close to 100 between what this does and what NVIDIA is doing today. Lots of computation, about 10 to the 16 equivalent flops at 20 watts average. Now, if you think about it, the energy per neuron activation, that's an interesting number. How much does it take me to fire a neuron? And actually, it's not too good. It's 250 picojoule. That's a lot of energy. So the brain is very hesitant to fire a neuron. Actually, at any point in time, if you have 100 hertz active space, it's 0.2% of the neurons are active at any given time. It's extremely sparse in its computation. Otherwise, the power goes up too much, and the system has to slow down. It has no way to remove that. Now, the good news is basically running your brain, and the energy cost per brain is actually pretty good. If I take a couple of hamburgers and things like that, that's your energy source, $10, $20 per day basically makes the thing run. Right? That's from an energetic perspective. So it's a very cheap type of structure overall. But the key properties, it's slow, it's not faster than it needs to be, very sparse. Sparsity is really important, and very local. Basically, computation and logic are next to each other, and memory, sorry.
That kind of goes against the fact, though, that you have a diameter of 3 and a fan out of 1,000.
Mm-hmm.
Like, that sounds like it's sort of not local, like everything's connected to everything everywhere.
That is correct, but it's local in the sense you don't have to go miles of distance to get a piece of information. Okay. Right, that's the locality we're talking about. You're right. Some of those wires can be relatively long. Some of those axons are really very long wires. The longest one that we have is a nerve that here is about a couple of meters. It goes to your legs, actually.
I mean, if the average diameter is 3, the average wire length has to be like, not wire, sorry, but it has to be 1/3 of the distance across your head. Right?
That is correct.
Or 6.
That is correct. And there's a bunch of very small ones, but there's long, long wires that basically connect multiple domains, basically. There's an interesting structure. If you look at the straight structure, it's kind of chaotic to a certain degree, but you have the columns in the cortex is a column structure, where you have the longer wires on top, basically, or no, at the bottom, they're basically wires to all the other ones, and then you have local wires at the higher levels of the stack, basically. Now, so we've been trying to mimic this, right? Very simply, we say, okay, we'll build a neuron, a very simple model of a neuron, and we could do many, many, many of those, build them in multiple layer networks. ChatGPT 400 layers of overall 1 trillion parameters. Think about the parameter as a synapse. So our real brain has 100 trillion of them, so a factor 100 difference between the two, and about 2 million neurons on a single chip. But then again, you can repeat it, and build bigger and bigger systems. Now the cost, if you compare it to my $10, here's your cost today. Now the interesting number that I kind of blew me apart when I first learned this, when I did the analysis, it actually turns out if you do a neuron activation on the NVIDIA H100, it also takes about 200, 300 picojoule, pretty much the same as my biological neuron. Same number, but you don't have the sparsity. These are massive networks where everything is firing out and firing out. So sparsity is the thing where basically the power explosion happens. So single forward inference step is about 40 joule. Training is about 80 to 160 joule for a forward and a backward pass, but you do a full training with the whole data set, it's about 0.4 telejoule or 100 megawatt hours. So the energy cost, remember $10 for the brain, $10 megadollars for basically one of those NVIDIA style environments, ChatGPT 4. So this is clearly not sustainable. We are now scaling it up and up and up and up. You know this is going to hit a brick wall. And you can do certain things about it. You can improve on it. You can try to think about being smart. Like you all know about DeepSeek. DeepSeek, the Chinese company that basically suddenly say, hey, we can do very much the same as ChatGPT, but we do this at a fraction of the cost. Energy cost 45. And what it boils down to is no rocket science in here. It's pure, quite good engineering. Optimization. You say, okay, let's get a little bit more sparse. Can we use sparsity to a certain extent? Can we basically reduce the precision? And how far can you drive it? Today, still for training, you need about floating point 8, which is still crazy to me because you have trillions of elements. You're operating on statistical information. It's a lot of noise, and you still need 8 bits. Kind of blows my mind. Our brain works with analog signals, which have a signal-to-noise ratio of approximately 1. But they have lots of them. And so you get popular encoding. So custom code, they basically had assembly programming, sparse mixture of experts, something like that, but 45. But again, I think we need to do a lot better than that. And I already mentioned neuromorphic computing. Again, there's a lot of progress in that space as well, where you build hardware that's, rather than transistors and digital gates, you build neurons and you connect them together. Intel has been a driver in this whole space. Loihi is the most advanced device in there, has about the complexity of an owl brain. You might have looked at the news this week. You've seen that another company has now built a neuromorphic system that has the complexity of a macaque monkey. So they're making progress from owls to monkeys, but that's a big step forward. But again, you see here the advantage is, again, it's 200 picojoule per neuron. Here they can actually do a lot better in terms of the energy efficiency of the device. So neuromorphic is an interesting thing to go. And don't only think about very big machines, neuromorphic also can work at the edge. There's some really beautiful work that people have been doing to show small networks that are basically embedded in sensors and things like that to get interesting type of thing going at very low power levels, spiking neural networks, and other style of neuromorphic, not only based on direct neurons, but for instance as oscillatory networks, electromagnetic reservoirs, things like that. So again, playing around with those new devices obviously challenges the way you're going to program it and use them, but it's an interesting thing to think about. The other part is, as I said, you can think about using biology or neurology as an example device. The other one is look at physics, all the way like what Feynman basically was talking about 60 years ago now. Basically use physics as computing. And if you think about optimization, for instance, this my colleague here in Berkeley, Eli Jablanovic, gave a talk at ISSC this year. It says, all optimization approaches are a version of physically based minimum entropy generation. So if I can build a machine that actually implement those things like icing machines, either optical or oscillator-based or photonic, you name it, you might be able to track basically large optimization problem a lot more efficiently than we do today in these data centers. The problem obviously with those things is it's great to get small demos, but scalability. Nobody has shown gigantic optimization problem being solved by this type of machine. But again, I don't say that's it's not possible. I believe it's possible. You also can mix neural with physics. So one of the classes of machine learning approaches is what's called physics informed, where the training is not done by simple backpropagation, but you actually put real differential equations and modeling certain parts, like for instance in this case, Navier-Stokes. So you can actually build a neural network that's inspired by physics equations and so on and so forth, being more effective. All right, and obviously there's one class of physics-based computing that we all know about, and it's right there. Everybody's talking about quantum computing today, and yeah, it's going somewhere. The nice thing about it, if you think about it from an efficiency perspective, it's really good. 10 to the minus 17 to 10 to the minus 15 joules per op, which is quite incredible. But unfortunately, to get that thing to run, you need a gigantic control system, you need a cooling system and things like that. So the power itself is very high. But as an accelerator, this thing makes perfect sense. And you will, I have no doubt in my mind, we'll see basically accelerators based on quantum happening very soon. Again, there's a lot of stepwise progress, and it's accelerating over the last couple of years. So that's one other opportunity to go forward. So, final thing is adaptivity and system intelligence. I have all those type of tricks I can play, but ultimately it all boils down to the same thing I mentioned earlier: compute the right thing at the right place at the right time and provide energy accordingly. That's kind of the system we need to think about. And we shouldn't think about just that single device, you think about the system at large. And again, very often there I look at, I'll come back to that in a minute. So here are some interesting people that are thinking about how to program the compute continuum, that big system. And here's kind of the interesting question. To fully realize the compute continuum potential, autonomous and proactive management is essential. Leveraging interdisciplinary methods from optimization theory, control theory, machine learning, artificial intelligence. So it's really bringing a whole bunch of disciplines together to make this happen. But the example I really use is, again, how our human body operates and our human brain operates. It's quite amazing that we have systems in place, metabolism and physiology, that basically do a couple of things. First of all, metabolism is to make sure that you have enough energy for growth, reproduction, and repair. Right? That's one thing. And the physiology looks basically how organs, tissues, and cells work together to maintain life and respond to changes in the environment. We have a really adaptive system that observes, measures, and then as a result reacts. And that feedback loop is something we need to think about at the large system level as well, dynamic systems and basically. So a very interesting challenge from a theoretical perspective and organizational perspective. And with that, I want to conclude. Here's kind of, again, my roadmap. We're here. We're going to see 3D, locality, sparsity, but ultimately new primitives and activity will basically be very important. And it will require innovation and inspiration. Thank you. Questions? Yes?
So, just going back to the $10 a day per person per hamburger versus DeepSeek, I didn't quite understand what the number that you had for DeepSeek seemed like 50 million or something. I didn't quite understand.
Okay, let me go back.
What that number was for.
Yeah, DeepSeek is here, right?
Yeah.
So the 45 is their cost. This is the training run. So you basically train one model, basically ChatGPT for, let's say as an example. That's where today a biggest part of the cost indeed goes to the training. And for a company like OpenAI, it costs them about $70 million to do one run. Every time they update the model, $70 million. And that's purely the energetic cost. The cost of energy that they run, all these computers. DeepSeek, because of the fact they are 45 times more efficient, basically their cost for running a model is a lot lower. Now, this might be a little bit misleading. So far, most of people have been talking about the cost for AI is going to be the training cost. And it has been true for a while. But nowadays, with success of everybody using basically their agents and so on and so forth, inference has skyrocketed. And today, the dominant cost has become inference. So actually, improving inference might become more important than training the model. But at the same time, though, the newer systems also train the model more often. They have the incremental learning. It's not anymore like you run the thing, you have your data, you run it one time, and then you release it. The models improve themselves almost on a continuous basis as well. So that also increases the cost of the training as well. But yeah, so the numbers are staggering, though. Again, those numbers of energy numbers is just blowing your mind. You say, this is not going to happen. We're not going to basically spend 50 or a couple of hundred nuclear plants just to run basically AI modeling. Yes?
have a question. So you talked a lot about how to learn from biology, mostly thinking about the brain, right? But the brain is a very centralized type of control structure.
Correct.
I know it's not fully centralized the way we operate, but
Correct.
still we have this centralized computing that tells us most of what we do every day. But a lot in biology is done in a very decentralized manner. And I mean, I do believe that decentralization does help a lot in reduce energy costs, et cetera, because you can make decisions that are purely local, but in a way that as a collective or whatever you have, it's going to induce the collective to behave a certain way.
Fully agree.
Do you have any thoughts about that?
Fully agree. And then again, if you take a big picture of the compute continuum, it's really a distributed system. Right? We're not thinking. I definitely don't think about here's this centralized intelligence and then it controls everything. Now, actually, distributing intelligence everywhere is really important. And you're totally right. Our body obviously has our centralized decision-making processes, but we have basically intelligence at all through the body, basically. And a lot of these processes are automatic. They basically adjust themselves automatically without having to go basically to the central computing center. And that's really, I think, a very good model also to think about how this large distributed compute system should work. You don't want to basically have a central controller.
And I think, I mean, I'm no expert in energy, no. But I do believe that it could help in that sense also.
Yes. There's some really beautiful books that are out there that basically, I'm trying to find the authors right now, the name, but it's an engineering perspective on how the brain works and how biology works. It's actually very beautifully written, and it's worth reading it. It's inspiring. And I think having that capability of cross-fertilization between the domains, now obviously they're not the same, but I think, for instance, one thing that I learned is if you think about how the brain basically does certain computations, it's actually a chemical machine to start with, right? Chemistry is very cheap. For instance, from a communication perspective, if the brain wants to get a signal to somewhere else, it just puts some proteins or whatever it is in your bloodstream, and it does broadcast. It broadcasts to everywhere, and only the parts that are interested are listening, but it doesn't cost anything. The communication is for free because your bloodstream is happening anyhow. So chemistry is the first layer of computation in our biological systems. And then we do electrical. Electrical comes in there as well, but it's analog, not digital. The digital levels only come at the higher levels when you have to do discrete decision making and so on and so forth. And this digital is a lot more expensive, orders of magnitude more expensive than what it would take to do something in the chemical base. So that whole interplay between electrochemistry and so on and so forth is an important part as well. Yes?
So I really like what you said about doing the right thing at the right place at the right time. So if I take it to one small example, let's say people have been working on circuits, go self-time circuits or asynchronous. Do you think they will have a future based on what you discussed here?
I've always been convinced that the whole synchronous approach is basically a waste of energy. It is. We spend a lot of time trying to basically to organize, basically distribute the clock system signal everywhere so that everybody agrees on the same time spot to do things. It's very expensive, and you look at digital chips of today, a lot of the energy goes just into that. Now, I think ultimately doing something at the right time and when data is available is exactly the right thing to do. The problem really is the methodology. We have been used, it's a very simple, the synchronous approach is very simple, right? Everything is based on a clock edge, and you have to make sure you're all done when the next clock comes in, and life is beautiful, right? And it basically orders the events, and it's a beautiful implementation, but it's expensive. And it's now built into our design methodology. So if you want to go self-timed or asynchronous or anything like that, you have to rethink your whole chip design methodology. And now you go to any company like Cadence or Synopsys and you start talking about this, they say, are you nuts? Ain't gonna happen. Unless we have a gigantic customer that says that they want it. I remember saying, this is exactly what Artegus And the CEO of Synopsys told me, I says, hey, you should really think about some self-time type of thing. I said, yeah, I like it a lot, and I totally agree with you, but we don't have big customers knocking on our door, so we're not going to do it. But if you think forward and think, indeed, if you look at a system perspective, these very large distributed systems, it doesn't make sense to impose a single clock on it. Basically, think about it. You do something, when the data is ready, you process it. So you basically self-regulate. To me, it's an obvious thing, but it will happen, probably not very soon.
Thank the speaker again. See you tomorrow at 8:30 or 9.
Yeah, I got an old friend here.